An op-amp is a differential amplifier, voltage type, with an infinite gain, an infinite input resistance, and a zero output resistance. That's an ideal op-amp. Non-ideal ones will have finite, but large voltage gains, finite but large input resistances, and low output resistances. The symbol for an op-amp is this triangle you see down below here. It's kind of shorthand for this model you see up above. The plus and the plus correspond, the minus and the minus correspond, and the output is at the point of the triangle. Now Mr. Blue here is a little bit worried about this op-amp model because whoever in his right mind wanted an infinite gain amplifier. Well, let's see if we can help Mr. Blue understand why this might be a good thing. It all has to do with a very nice thing called negative feedback, which we will actually spend a whole chapter on toward the end of this class, or perhaps at the very beginning of Electronics 2. Here is a block diagram on the bottom that shows a negative feedback. Notice the block A here, that corresponds to the op-amp. VI is the V plus minus V minus, the input voltage to the op-amp. VO is the output of the op-amp. This beta is something we have to add to the op-amp, and it's going to take a small portion of the output, and it's going to put it out over here in a place that's going to subtract from the actual input to the whole circuit, and that's going to give us the input to our op-amp. We'll see how that works in a little bit. At this point, let's just see if we could actually make this block diagram here. How would it help us? And that really requires doing just a little bit of algebra. So if you notice from the diagram here, V out equals A times VI. And VI equals Vs minus Vf. But Vf equals beta V out. So if you put all those things together, you end up with V out equals A times the quantity Vs minus beta V out. This equation can be solved for V out to yield V out equals A times Vs over 1 plus beta A. Notice that the gain of this thing is V out over Vs, it's A over 1 plus beta A. So the gain was cut down by a factor of 1 plus beta A. And, as long as that's bigger than 1, it cut the gain down somewhat. Also notice that the input voltage right here, known as the error voltage, can be written as V out divided by A. And if you do that down here, V out divided by A, you get Vs over 1 plus beta A. It just divides that A on top out. Now let's look at the limit as A goes to infinity, because remember that's what our ideal op-amps were hoping to do. So if we take that limit, the limit of this gain right here as A goes to infinity gives you just 1 over beta. And the limit of this error voltage as A goes to infinity goes to 0. So the error voltage goes to 0, and the output of the op-amp might actually possibly be something reasonable, because this number A over 1 plus beta A is not an infinite number. It's just 1 over beta in this case. And beta, we could set beta equals, say, 0.5, and we could get a gain of 2. So next, let's try and concentrate about how we might take this block diagram, which is doing kind of what we want it to do, and make a circuit that behaves exactly like it does. So let's start with the input part here, the summing part. Vi is equal to Vs minus Vf. Well, the thing I know is Kirchhoff voltage law tells me that if you have an input voltage or any voltage here, it's the voltage at the positive terminal minus the voltage at the negative terminal. So this says Vi equals Vs minus Vf. So that's why I arranged the Vs and the Vf here around the Vi in this way. So we've now come up with something that does this sum for us, Kirchhoff himself. Now what I'd like to do is concentrate on this part of the network, because we have to add that to the op-amp as well. Now this remember we wanted V out to be something like a half of, VF to be something like a half of V out. So let's look at how could we do that. Maybe something like a voltage divider. That could cut the voltage in half. So if I make a voltage divider here where V out is the input and VF is the output, voila, yeah, all I have to do is make these equal resistors and I'd get a half as the ratio. And remember, if A went to infinity, V out over Vs was 1 over beta, and so the gain here in this case would be 1 over beta, beta being the voltage divider ratio up here, so it's just R1 plus R2 over R1, which is actually any positive number greater than 1. So this new system right here is a voltage-controlled voltage amplifier. It's a voltage input, voltage output, a voltage amplifier, and it has an infinite input resistance because remember no current goes into the op amp, so no current is taken from the Vs here, and a zero output resistance because this voltage right here was defined to be, it has to be this ratio right here, which by the way is only a function of resistors. And it turns out that resistors are probably the best electronic component we have. They are very, very linear, and they work like a resistor until they blow up, which is, you got to do a lot to blow up a resistor. So it's very much easier to make this thing work. All I have to do is make this gain large here in this circuit, and then it's only a function. The gain of the feedback circuit is only a function of these resistors, which I could get to be 1% resistors, and I can have a pretty accurate gain. Now let's see if we can come up with some rules for analyzing op-amp circuits like this one. So the first rule I came up with was no current flows into or out of the plus and minus input terminals. Why is that? Well, that's because in our original model there was an infinite input resistance. Remember back up here, this Ri was infinity, went to infinity, so that means it's open circuit, so no current flows in the V+, likewise no current flows in the V-. So that was the first rule that we needed. The next rule is if negative feedback exists and no positive feedback, in other words, if we have a block diagram that's like this, then this input voltage is driven to 0. And so in that case, we can say the input voltage here is 0, and that can be handy for analyzing circuits like this. The last rule right here is write node equations at each input terminal, never at the output. Now this isn't the only way to do it, it's just a hint. This isn't really a rule, it's just a hint that helps people. So let's try and apply these things to this circuit which we came up with just a few minutes ago. So if we apply the first rule, it says no current is flowing in here. Well, that doesn't tell us much except that there's no current flowing through the source, which is nice, but doesn't really help us figure out what the output voltage is in terms of the input voltage. And it also says there's no current flowing in this point right here into the negative terminal. And then the second rule says, since we have negative feedback, you can see essentially you have negative feedback whenever there is some component connecting the output back to the negative terminal. And you don't have positive feedback as long as there's no component from the output going back to the positive terminal. So we have negative feedback here. And in that case, it says Vi is 0. When if Vi is 0, that says Vf equals Vs. And Vf is right here, so I'm just going to call this voltage, instead of calling it Vf, I'm going to call it Vs. And I'm going to write a node equation right here at this node. So first of all, there's no current going back in here by rule number 1. The current going down through R1 is just Vs divided by R1, because Vf is Vs here. And that's the first term down here in this node equation. The next current is the current going from this node up here, which is Vf minus V out, and Vf was Vs, so Vs minus V out over R2. So that's this term right here in the equation. And we add all those currents up, those three currents, 0 plus this one, and I get 0. Solving this equation using algebra, you end up with our old friend here.